The Compton effect refers to the observed relationship between the wavelength of a photon scattered by a stationary target and the scattering angle. The observed effect is consistent with the equation lambda prime minus lambda equals h over mc times the quantity 1 minus cosine theta. Lambda prime is defined as the wavelength of the scattered photon. Lambda is defined as the wavelength of the incident photon. H is defined as Planck's constant. M is defined as the mass of the particle. C is defined as the speed of light. Theta is defined as the scattering angle. For our derivation, we will make the following definitions. In the laboratory frame, the particle is initially at rest. Let capital P represent the momentum of the particle after collision. Let lowercase p represent the momentum of the incident photon. Let nu represent the frequency of the incident photon. Let lowercase p prime represent the momentum of the scattered photon. Let nu prime represent the frequency of the scattered photon. Now we apply the conservation of energy. The energy of the incident photon is h nu. The energy of the scattered photon is h nu prime. The energy of the particle before the collision is the relativistic rest energy mc squared. The energy of the particle after the collision is given by the relativistic expression square root of the quantity m squared c fourth plus capital P squared c squared. Therefore, h nu plus mc squared must equal h nu prime plus square root of the quantity m squared c fourth plus capital P squared c squared. First we isolate the radical and then square both sides. Rearranging again to isolate p squared c squared and then dividing through by c squared yields an equation for p squared. Now we make note that h nu over c is the momentum of the incident photon, and similarly for the scattered photon. This yields a more compact expression, which we will compare to an expression derived from conservation of momentum. Expanding the polynomial term, we can cancel m squared c squared, yielding our reduced expression, capital P squared equals p squared plus p prime squared minus 2p prime plus 2mc times the quantity p minus p prime. Next, we examine the conservation of momentum. Initially, we have a particle at rest. This means that the incident photon carries all of the initial momentum. Post-collision, we have the scattered photon and a presumably moving particle. Therefore, the vector lowercase p must equal the vector sum of p prime and capital P. We can rearrange that to say capital P must equal the vector difference of p and p prime. To eliminate the vectors, we take the scalar product of each side with itself. Applying the definition of the scalar product, we get the reduced expression capital P squared equals p squared plus p prime squared minus 2p p prime cosine theta. Now, to eliminate the particle's momentum, we examine our reduced expressions together. From the conservation of energy, we found that capital P squared equals P squared plus P prime squared minus 2P P prime plus 2mc times the quantity P minus P prime. From conservation of momentum, we found that capital P squared equals P squared plus P prime squared minus 2P P prime cosine theta. Equating these expressions, we can cancel P squared and P prime squared from both sides and eliminate a constant by dividing through by 1/2. Rearranging gives us the expression mc times the quantity P minus P prime equals P P prime minus P P prime cosine theta. Dividing through by mc and factoring the right side, we get. Now we observe that since P equals h nu over c and nu equals c over lambda, we have P equals h over lambda, and similarly for P prime. Substituting for P and P prime, we get now multiplying through by lambda lambda prime over h, we get the Compton equation.